Okay, welcome all of you to the live session. I think this is the last live session that we are going to have for this term. So, if you have any questions regarding the homeworks, any conceptual clarity that you need based on the contents of the course, or possibly some guidelines into the exam, feel free to ask these questions. Uh, we have the 40 years as well here. Okay. Do you have an idea how many people have logged in? Yeah. So I have one question here by Dr. Anil Wanare, faculty. His question is basis function. Seems to be very broad. Right? I think this is basically the first few lectures of the course. Uh, so what is a basis function? Like the way you have basis vectors, yeah, you can kind of extend this to basis functions, right? They are linearly um, dependent and they span the space of the signal. Right? From signal space, it spans and they are linearly dependent and they form a basis. So a simple example is if you think about the coordinates, the vector I and vector j on a two-dimensional Cartesian plane, you can think about these coordinate axes to be functions. For example, if I have space of uh, cosines and sines, I can for just a single harmonic cos x and sin x, I can think of cos x and sin x that I can represent um, basis, right? So this is an analogy. Whatever we think in terms of vectors, we can think in terms of functions, and vectors they span the vector space, and basis basically span the signal space. Right? And I don't know what is your specific question on basis function. If you have some more clarity into what you really want, then we can go further into. People are joining in, 4 people. Just incremented from 2 to 4. feel free to ask questions. I mean, if you have questions on the assignments or solutions or anything, you can ask. We have the TS as well here, so we can take up those questions. Any clarity that you have on any question, we can take it up. We could do that. Well, at least sometime, half an hour. They have them and just give a quick recall of everything. That question from the exam. You want me to discuss this here? So you can ask this question and I can take this up on their behalf. I can answer live.
A lot of students actually wanted to know about the exam, like how
Examination
what
pattern.
is the examination pattern, what they have to
Okay.
study, how to.
Okay. So this examination is an online exam, a computer-based exam. So there would be questions, and most of the questions could be, there will be multiple choice or true false or entering some numerics, etc. So there will be a problem. You may have to solve something and then enter the punching the number, or it may be true false question whether you have to select true or false, or it can be multiple choice where one answer will be correct or more than one answer could be possibly correct, and you have to tick all the correct answers to get the full score, and you will be partially graded based upon the choices that you have. So I think there is, so that it's going to be that, and it is going to be a comprehensive exam, and you can imagine that it is going to cover the gamut of the syllabus, right? So initially we had linear algebra, then we went to probability, stochastic processes, then we moved into filter banks and these ideas, and then the wavelet transforms, and then KL, and then Fourier convergence issues as well. So I think all these topics would be covered. So I can't say which to emphasize or what. So that it is comprehensive. So the paper would cover all these. So in some cases there may be problems where there may be, some 4 or 5 problems can be linked to the same concept. In some cases the problems can be independent. Just it is standalone kind of thing where you have to solve it and then that's it. So I think that's what it's going to be, and it is. I don't think it will be too computationally intensive. It requires more of your thought, careful work than just doing a lot of intense calculations or whatever. So I don't think that is expected. But I think to follow whatever are the guidelines given to you, like when your calculator and other things, this is something expected. I don't think there is any cheat sheet allowed, right? There's nothing just, so these are your general guidelines. So my feeling is if you've solved all the assignment problems, so look through all the assignment problems, and you should, before you come to the exam, you should be ready to at least, without seeing the solutions, be able to answer the questions yourself from the assignments, right? If you can do that, I think you're sort of prepared. And if you still require help of solutions to refer to the questions and then be able to solve, then I think that shows your weakness in certain areas. You have to brush up, look at the slides, etc. And there's also my course which I offer at IASC, and there's a whole lot of questions there. You can take a look at those questions and you can kind of prepare yourself. So I think it gives you an idea what to look for, right? So, but beyond that, we don't know what question is going to come, what is going to be computer and test. But I think look into the concept. That's the most important thing. I think um, conceptual clarity is very important for these type of courses. It's just not routine algebra and doing something, bunching numbers. I think if you're clear in the concept, then you think you'll be able to answer the questions. And you should be familiar with ideas like stationarity, fixed sense, wide sense, all these type of ideas, random processes, computing moments or mean, variance, etc. You should be knowing, checking for independence, etc., statistical independence or linear independence. You're familiar with all these ideas. If not, then you will be in trouble because you don't have a crib sheet to carry with you, right? So that's difficult. So you should know all these ideas and what really you need to enter the exam hall because you can't refer to any notes. So you should be remembering these things. Ready. Did we have any other questions from them? We'll give some time. We'll go another half an hour. If nobody is there, no questions, then we can end it early. Right? 7.5 hours. And any questions they have, we can take it offline. Not a problem.
The live session asked us three questions.
Okay. Can you
First,
state the questions? Yeah.
first question is by Dr. Santosh Kumar.
Mhm.
The question is about 5G applications.
Oh, it's too broad. Your question is too broad. 5G has a complete, it's a standard. It has a lot of details where you want connectivity of every device to everything else. So I can't answer that in this as a part of this course. So I suggest you look through the upcoming standards for 5G. I am myself not in the standards committee for 5G. So look into the details on 5G platforms, etc. And then if there are any specific question, I may be able to answer if it is within the purview. So I myself am not very familiar with all the details of the emerging 5G standard. So to broad a question, I think someone who is handling wireless communication course can probably give more insight to 5G. So I think we can skip this part because yeah.
Next question is by S. Pravina Sedu. Which is, what is the need of interpolator after QPSK modulator in communication?
I don't know what specific block diagram you have in mind for this interpolator and for QPS. What is the patient keying modulation that you have, right? In phase or 90 degrees phase, and you modulate the signal. And I don't know what you're doing post that when you bring in the interpolator. So I would like to know more specifics of your block diagram. What is the type of communication system? Whether you're sampling at that point, or I need to know more details. So this again seems to be vague because I don't know what is the block diagram you have in mind, what is the application you have in mind, and then what is the need. So I can always put some interpolator. I know what is the reason for this. So, lack of clarity.
Next question by the same person is, sir, please suggest some textbook for wavelengths.
So there are plenty of good textbooks for wavelets. I think a good book would be a very good book would be the book by Elena Kovacevic and Martin Vetterli. So they have discussed they bringing this notion from signal space and go all the way into the details of constructing R wavelets, other wavelets, and including the wavelet packets. So this is an excellent book to refer to. There are also these traditional books, for example, the classic book by Ingrid Dubushi on 10 lectures on wavelets. This is a very good book. There are also books by Cohen and others. So you can take a look at these books. But I would suggest the book by Vetterli and Kovacevic. It's a fairly comprehensive book, quite well written for the graduate level understanding. I think you'll find it. But there is also treatment on wavelets in various other books, from mathematics to engineering and applications. So plenty of books are there. Do you have any other questions, maybe from the videos or anything that they have unanswered or whatever? I'm more than happy to take this. Hmm?
So,
Initially, actually, there were a lot of questions on them. We answered all.
Okay.
We could just get it in.
once maybe when
What
actually
exactly they are.
people are maybe confused about
Modes of a linear
and
system.
just
Okay, the modes are essentially like, if you look at the, I would start with basic mathematics, right? If I give you, say, a homogeneous equation and I like the d square plus 3d plus 2 equal to 0, and I want to look at how the behavior of this differential function, what is the solution to this, right? Without the particular solution, the complementary solution. So then you will say that you look at the roots of this polynomial and factorize, and then you will say this is, let us say you take d square plus 3d plus 2 equal to 0. This is d plus 2 times d plus 1 equal to 0. So basically d equals minus 2 and minus 1 of the roots. This is c1 e power minus 2t plus c2 e power minus t. These are the modes. Basically, these are like um, the modes are like the roots of the homogeneous equation that you have, and they control the dynamics or behavior of the system. This is what they are. So they are also the eigen. They're also called eigenmodes because they're typical. They are the natural modes of the dynamical system, of a linear dynamical system, more precisely. And the same idea you can extend it to the discrete time space where you have a difference equation, governing difference equation, linear difference equation, and then you solve for this. And related to these modes would be this dominant mode. I mean, the largest eigenvalue would be the dominant mode, and would be would be less dominant. I mean, one which is the largest value that is a dominant mode, everything, and that would determine by far the behavior of the linear dynamical system than the rest. So I think this hopefully should clarify what the origins are basically from your differential equations. If you even start with a simple spring mass damping system, right? You have md square x by dt square uh, plus your damping constant times dx by dt plus kx equal to 0, and you look at the system. If you give a force, an impulse, to the mass and you let it go, there are some oscillations that can decay or that can sustain or whatever, depending upon the frequency you give. And the nature of the damping constant, spring constant, and the mass will determine the output of this, what exactly what in signal processing. There will be another thing, is it? We'll give another 10-15 minutes, then we can just wrap it up. Then we'll give us an overview of the whole thing and that sort of summarize course. We'll give another 10 minutes, then we do this overview. Yeah, from next time onwards, what we can do is we can have a planned live session that is also called, and we can schedule it so that people are kind of well aware of times and they can basically mark their calendars for these parts. That may help you to plan this a little better. So we can do. Okay, we have some questions. The electric vehicles emit heat like cell phones. There should be some dissipation. Right? There should be something. Any because you don't have 100% utilization of energy anywhere with an electrical circuit. There should be dissipation. Moving parts, mechanical parts. The efficiencies are not 100% when you couple systems. So, yeah, heat loss, yes. Any resistance loss, it is going to go out. So, yes. Electric vehicles are no different, except that this thing is clean. Instead of burning the fuel and stuff like that, you don't do this carbon emission. So that you would eliminate, provided you can charge your vehicles at every station. But I don't know what is the link to signal processing and this question for electric vehicles. But I see signal processing to be up. You can think of applications to electric vehicles. But your question and this course, I think, they are. But yeah, but still, I hope I answered your question. Answered your question. Yeah, feel free to ask questions, however silly or stupid it is, because it is better to be stupid now than be on the exam. So if you have any questions which you have that that however basic it is, don't shy, just ask those questions. It's better to be clarified now than wait after the course is over. And how has been the performance? I think I just had a snapshot of the average scores out of 100. It seems to be around 50, 50-ish. So I think students who are watching this, if you have any questions regarding the homeworks or the difficulty level, you can ask, maybe clarify. Maybe the first time you're working it out, you find it hard, but at least for the exam, you should be comfortable. And another question: if all people in the country will use electric vehicles, temperature of the environment will increase or not? It should be additive, right? It should be additive, right? Anywhere there is energy consumption, there should be some dissipation, some loss. Yeah, of course, it should. But see, the impact on the environment and everything has an impact on the environment. From the roads that you build to the cities that you have, everything has an impact on the environment because it's a closed loop control system, right? So, but how impacting it is because nature has its own way of regulation. Because there is from the ocean you get this air and there is the cycling of hot air and cold air and exchanges which happen, which tend to balance things out. But yeah, there would be some impact. The question is whether it's one way it is, yeah, you don't put the carbon emission out, but you're using clean energy, but it has its ramifications in terms of electric efficiency. That's what you have to look for, how to harness this energy and make it clean, that you don't dissipate energy very long. Like your good example is your air conditioning. Don't you think you're going to give heat back to the environment because you stay cool inside? This is an exchange, right? So you can't. It's the same way.
Just another temperature will increase. So here, solar influx, sun,
So
energy from
it's a
sun is
complicated
always
modeling,
always
right? I
coming.
mean, yes,
It
but
is dissipated back to the atmosphere, right?
yeah, the atmosphere
But
should have its own way to self-regulate. So I think more than the electric vehicles, I would even look at smart cities and the way this heat radiation is happening everywhere because of loss of the green cover and all that. I think that is more, I feel, is more impacting because the water table doesn't. I mean, you're not asking a question related to mathematical methods. It is more on a public policy. But I'm happy to take this question for you. But there's a cycle. There's an equilibrium to the systems, and I think one has to be within the equilibrium. Otherwise, you always have problems. Water table going quite low, or the excess radiation heat that you have because of all these concrete roads without the green cover. So that will have an impact. You will not see it now, but it's going to be additive. Over years or decades, you will see this impact. I think these are more pressing problems than, I would say, electric vehicles. Electric vehicles are relatively, I think it's a good alternative than your normal um, fuel, right? Diesel or petrol or gasoline. Yeah, increase or not, it should increase. You can measure it. It is depending on where you measure. If there are no questions, and I think let us look at the summary. Right? Maybe do you want the TS to do this sort of, or you want me employing? Huh? TS want to add something to it, you could. You could just take turns and you could speak into the microphone because you have handled these questions as well, and if you think what could be emphasized, it's also perfectly fine. We can take turns. Maybe let me give a snapshot of the overview of the course, and then maybe the TS can comment as to what they felt in certain assignments, etc. You have topical, topic-wise, you've seen these assignments and performance, etc. TS can comment on common issues, what they found and what you could remedy towards the exam. Okay, I don't have the syllabus at the top of my head, but can you share me your laptop? So I have the laptop in front of me here. The course layout began as follows. Week 1 was review of vector spaces. So I think you should understand the progression between how you construct these spaces, right? You have these vector spaces, and then you endow them with an inner product, and you have these inner product spaces, and then you bring in this limit of the function or the vector to be part of that space, and for which you bring in a notion of inverse space and so on. So you have this notion of extensions through definitions. So basic vector space to a norm, and then from a norm space to inner product space, and then a Hilbert space. And one of the important things is orthogonality. I think this is something that you have to bear in mind, that it is much easier using orthogonal functions because orthogonality implies linear independence. This is a very important thing. Therefore, you can, using orthogonal functions, you can construct having orthogonal basis, which basically can they're linearly independent and they can span the space. You can basically represent signals or vectors for this. Then you have this notion of, so I think you should be comfortable with it, and taking orthogonal projections is very important because you have this coordinate representation that can stem from that. So the whole idea about physical geometry is basically to be able to represent the signal as a point in a signal space. So then we look into state variable representations is very important. Like the way we have done in control systems, the same extension can be thought about in the signal processing framework, except that you don't have continuous time system. Here we have discrete time system, and you can look at the output of each of the tabulas and assign them as your state variables and basically construct your state variable representation in terms of your ABCD parameters. So you can think about multi-input, multi-output, and these things um, are natural extensions. So week 2 was with a review of probability and random processes. This can be a separate course by itself. Even the week 1 course, which is basically linear algebra, can be a course by itself. But of course, we wanted to compress it to a point where we could get to signals, right? So you have to be comfortable with basic probability and random processes. Probability, what is random variable, then your moments and moment generating function, etc., etc. You should be comfortable with all this. Then in random processes, you should know how, if it's basically a waveform in time, but if you slice on time, you have a random variable. Otherwise, if you fix a random variable, it's just an ordinary function in time. I think if you get this idea clear, I think the rest of it is very easy to analyze. You can you hear me, Mahesh? I see that you're mentioning my voice is not clear. Can you hear me now? If you can quickly type in yes, then I would be satisfied. Okay. So we looked into this a review of probability and random processes. So in random processes, some of the concepts that are important and you should know is stationarity, right? When if you look at the statistics, the displacement of time, it should be the same. That if you look at all the moments, second moment, so on and so forth. And there's also this notion of wide sense stationarity, where your mean is constant autocorrelation depends only on the time lag. So you should be in a position to compute these things for certain waveforms and be able to ascertain if it is wide sense or strict sense. There are other notions of stationarity like cyclostationarity, etc. And we deal with this in communication systems, and I don't want to talk about it, of course. So the third week was on civil geometry and applications. So this is very, very important. I think it's very important from the presentation perspective. You should know how to represent a signal as a point in a signal space, and for that you need Gram-Schmidt ortho normalization procedure. You should be comfortable in doing this procedure and get the basis from your signals, and from then basically with the projections you can represent the signals in the signal space. Week 4 was in sampling theorems, and then multi-rate ideas on decimation, expansion, time frequency effects. So the sampling is very important. I mean, what it takes to have an analog signal, sample it, the sampling theorem, this rate greater than twice the maximum frequency and the implications. You should be comfortable with those. And then the interpolation, ideal interpolation, based upon the Shannon weighted interpolation formula. You should be comfortable with that using the sync function. And then we started with this decimation and expansion, where you are reducing you have the samples, you reduce the sampling rate, you throw away alternating samples, for m equals 2 or for m equals 3, you retain 1 in m samples, 1 in 3, m equals 3, and so on. In general, 1 in m samples you retain, and interpolation and expansion, you should be comfortable with that. So expansion is you restore the sampling rate by inserting zeros, and interpolation follows post that. So this thing you should be comfortable with. So we saw the time and frequency domain effects. So I would like you to look through these slides, through the videos, to be comfortable with the derivations, time and frequency. Week 5 was on sampling rate conversion. I think it's an important application. And when we want to look at, let's say I have a 48 kilobits per second, I want to convert it into, say, 90 kilobits per second, or maybe 48 to some other rate, right? Where there's a rational sampling rate conversion, L by M sampling rate conversion. So you should know what to do with decimation, what to do with expansion. Of course, everything abides by the sampling theory, right? We cannot do some conversion which is where you lose the maximum frequency of the original signal, right? We cannot do that. So you should be comfortable with those. And then we saw these efficient architectures for doing that, and for which we had to look at a series of interesting ideas like the Nobel identities, then exchange of these systems. When L and M are co-prime, then you can exchange the downsamplers and upsamplers and stuff like that. We saw these interconnected systems, Nobel identities, and all these led us towards efficient architectures. And we also discussed the design of high decimation interpolation filter. This is very important. So what happens when you do decimation? You're losing the sampling rate, but in the frequency, basically there is a stretch. And this idea should be very clear, because when there's a stretch, that means you can choose filter orders that can work with than have steep filters, and that's one of the practical applications of using high decimation filters. Okay, so this idea should be clear in your mind. Similarly for interpolation filters, and then we saw these multi-stage designs. That means I want to just downsample by some rate or upsample by certain rate. It cannot be possible, and design filters like those. So I might want to decouple this problem into individual stage by stage design, and I have better control there by controlling the order of the filter. And also, if I'm clever enough, I can basically remove the aliasing error that can come through these multi-stage designs. So the examples are very clear in the videos, and I think you should be comfortable with doing any problems related to it. So then we looked into this two-channel quadrature mirror filter bank. So basic idea is you take and pass them to low pass and high pass filters, followed by downsamplers. And at that stage, you can do quantization, coding, and compression, whatever you want to do. And post that, you upsample, restore the sampling rate, get them to the synthesis filters and recombine them. Right? Ideally, without any quantization, you should have perfect reconstruction, provided you design your synthesis filters uh, to cancel the aliasing effects. Right? I mean, you have aliasing distortion, you can have amplitude distortion, you can have phase distortion, you can compensate for various distortions using your choice of filters. But the compression really will happen when you do quantization post the downsamplers. So at that stage, you should be comfortable. That's typically how subband coding is done. And this is the standard for the MPEG 4 and generations beyond that. So you should be comfortable to be able to do quantization and then an appropriate compression engine to the level of bit error rate that you want to, and that there's a compromise on the quality of the signal post reconstruction. Then we discussed the M-channel filter bank as a natural generalization of the two-channel filter bank. Then we saw how we can overcome aliasing errors, amplitude, and phase distortions. And phase distortion is very important. The practical aspect of phase distortion is imagine you have this a video sequence, a movie, where there is a song on one side and an image on the other side. So if there is, it has to be phase aligned, right? I mean, your voice and your singing, or if there is a sequence, or your speech, etc. There should be a sequence to that. I mean, so it has to be phase aligned. I mean, the voice and the picture should be phase aligned. If not, if the voice has a different phase and the picture, the motion has a different phase, then it's basically garbage. It's like things are not coherent, right? So I think these are very important ideas, and you will see this in the practical design of such systems. So you don't compensate phase distortion, and if you don't have linear phase that you can control, you will have all kinds of problems. So then we looked into these subband coding ideas and filter designs and signal compression. I just covered the idea that you can do quantization and encoder, source coder, or entropy based, or it could be transform based coder at the source towards getting your compression. So with that, the filter bank theory is nicely linked with wavelets, and we saw these connections. So I basically covered what the ideas are for multi-resolution analysis, that you can go to whatever resolution that you want to, and you can decompose the signal. That's the power of wavelets. Then what you can do with the Fourier, right? And this you should be very clear in your head. The discrete Fourier transform will give equal resolution in frequency. That is, all the frequencies have the same resolution. But with wavelets, you can go to whatever resolution that you want, and then you can expand your function. And this is a very, very important idea that leads to this notion of multi-resolution. You have nested signal spaces, and then and you can go to whatever level of scale that you want, and you can expand the signal. And we saw this decomposition and reconstruction. We studied the Haar wavelets. Of course, you can think about other wavelets too. In the course, we covered only Haar wavelets, the simplest wavelet. And we looked at the decomposition using Haar and the reconstruction, and applications for denoising. It's a very important application. You can look through the slides, how you can have spike, how you can go to that level, and you can remove that spike at whatever burst length that you have, 5 milliseconds, 10 milliseconds, depending upon your application. You can zoom onto the spike and you can denoise. It's a very important application. Then, so this idea of wavelet is also another representation. Signal geometry plays a role here. Then we looked into KN transformation. So all the transforms we had earlier were all signal independent, right? Give me any signal, as long as I meet certain conditions, I can expand the signal, right? In terms of relative integrity, etc. These are some of the conditions that were posed. But with KN, it's data dependent. That means, they give me the data. If I want a linear transformation, which preserves the energy, of the data, and I want a representation in this space which basically compacts the energy into the first n coordinates. And if I set this up into an optimization problem and I solve for it, I get decay terms. So this is identical, put in a nutshell. And this has tremendous applications in machine learning. I mean, one of the first few algorithms that you will learn in machine learning, simple component analysis. So we looked at the derivation of the KL. There are plenty of applications from the bioengineering space to any data science space. So then week 11, we looked into topics of matrix calculus because we had to set up the scale as a constraint optimization problem, and the matrix calculus was useful for us. And you have this denominator format and the numerator format, and stick to one of the formats and do your calculus consistent to that. So I just had half an hour or 40 minutes of discussion on matrix calculus. So one can spend actually, several hours on this, looking at more complicated functions and extend the same notion of what you learned in differential calculus to matrix. But I just covered basic, essential details that could be of use in the course, and I'm comfortable with those. I'm fine with it. The last week was on the Fourier expansion and certainly showed the notions of convergence point, convergence point of continuity and discontinuity, what it is, and implications in the AIT sense, etc. So you should be comfortable with these various notions of convergence, basically starting with continuity, convergence, and basically what you would do to have this expansion sort of valid. For your expansion to be valid, I think this is an important question to ask. Under what conditions it is valid? How does it converge? What is the rate of convergence? These issues are, I think, are addressed in those video lectures. Okay, so you should be comfortable with all of these ideas, and so this basically is a wrapper in 15 minutes what you learned in 30 hours. So you should know these ideas. You should know at least conceptually before you enter the examination hall. You should know to represent a point in a sequence space. You should know what ideas of Whiteson stationarity or Strickson stationarity is. Some basic ideas on random variables you should know. The functions on these random variables. You should be comfortable. Then multi-rate operations you should know. Wavelet, you should be able to expand a signal using wavelet transform. Right? You should know about denoising. Then AL, you should be able to compute covariance matrices, blah blah blah, and then compute the eigen decomposition from that. Right? Get your eigenvalues and eigenvectors. So if you cannot do this, then I think you are not ready to take the exam. So you should know, because you don't have any notes that you can carry or videos that you can see, unlike your homeworks, and you can't discuss. So if you forget a formula, then I'm sorry, you cannot. Right? So be comfortable. You have to memorize many things, but I think along with the memory, conceptual clarity is very important. To be very, very clear about the ideas and how they work. If you forget even something, you can rederive. It is not advisable on exam to rederive because of time, but at least if you worked it out carefully, you'll be able to do this on the exam. And of course, Fourier expansion and the notions of convergence. So go through all these details, read through the videos again, jot down, make your notes, look at all your homework problems, see where you have faltered, where you have lacked clarity, where you went wrong, where you have gone wrong, right? And I suggest that don't again look back into solutions. Redo the problem yourself and then look into the solution. If it's a silly error, it's tolerable, but should not do silly errors also on the exam, because there is no way that we can subjectively grade your scripts because the computer does the grading for you. So therefore, you should avoid these silly errors as much as possible. But along with it, I think the main thing is conceptual clarity. Because if you are conceptually clear, I think you should be able to breeze through the exam. Of course, you should remember the basic concepts. Okay, so I think this would summarize the course. I think we enjoyed having you here. We took many questions. I'll answer some of those questions. I think you have one question which is not addressed there. Uh, I'll answer the questions that I did not address. But if you have any questions on the course or the exam, you can ask me now. Otherwise, we will close that discussion thread. Right. So don't panic. You may see a situation which is not on the homework, which is not there on the slide, which can be an application problem. So I don't panic. Just sit down, carefully think. I think you will be able to answer the question. There's nothing that we are giving you on the exam that is not tested or that is not dealt with in the video. Okay, so I think that is to be made very clear. So just stay calm and do the exam well. I want you to all do well and get good scores and good certificates. That's what we want. But you have to earn your grade. That's the most important. Right? Then we give you a grade. You have to earn the grade. So if there are any questions, you can type it. Otherwise, we can take some questions that you have. So Raju again, is this radiation will affect on the health of the people? You're asking me a lot of public policy questions than MMTSP. I wish I would, but I'll answer your questions. The cell phone towers. I mean, this is a proper. This is something which you can observe. But at least I see this in Bangalore. So, of course, there's nothing to do with mathematical methods and techniques in signal processing, but a general question. But maybe since all of you are engineers or scientists or whatever, you may want to think about it. So I don't know if you have noticed, I don't know which part of India you are from, Raju, but at least in Bangalore, I don't see sparrows. At least in the main parts of the city, I don't see sparrows anymore. There are two questions to this, to the two at least pointers to this, that there are a lot of cell phone radiations and these things which are basically, these birds are very sensitive to to radiations, and they're not. And also because of certain, they also don't find grains. And you see sparrows and pigeons and, the parrots are more, so if you go slightly outskirts towards the villages, you find them. So yes, there can be these effects that one can be sensitive to. So I don't know. Therefore, having too many such cell towers in a locality, of course, you get very good signal strength, and your mobile is having 5 stars signal strength, but there can be such effects, right? And if you just observe around you, the bird population, etc., and other things, I think this can be. I think it would be something to worry about. I'm sure this is a problem anywhere you go to. I'm not talking about, because I reside in Bangalore, so I can comment on things. Sure, you go to any other metropolitan city, you observe around it or ask the people around what is the impact. You may see this. So I cannot answer what this impact would have in 10 years or 15 years, 20 years. I don't know. But this is in general, yes, too much usage of electronic equipment and all these type of things, and high signal power type of devices, I think is not good in general. But we live in a very connected world, so I don't know how to answer this. This is more a public policy regulation question. So I can only tell you that yes, would it affect the health of people? Yes, over time. If you put too many if you put cell towers on your phone and on your home, and you want to get the best signal strength, I'm sure there will be radiation effects. So I hope I answered that question. Right? But unrelated to this course, but as a public policy or a general question, general knowledge question, yes, it does. Mukesh has another question. Is it useful to GATE 2020? I have no idea about. I can answer your question related to the course. I have no idea about GATE 2020 or what the GATE paper or who is setting the paper. I have no idea. But I can tell you, if you have mastered this course, because it's a graduate level course in signal processing, hopefully you should be able to address questions in signal processing areas in GATE. I mean, if you have done this course, is at a graduate level. This is not an undergraduate level course. It's a graduate level course, right? So if you've done this graduate level course in signal theory and you are comfortable with it, hopefully, I don't know, your GATE or any UPSC or any other competitive examination that you take in India or outside India or wherever it is, so you should be comfortable doing this course. Or you take advanced course, you should be comfortable. I don't know about GATE 2020. I can't answer your question. That is useful. You figure out. You have the syllabus for GATE 2020. Look at the content. Look at what this course offers. See if there's an overlap or not. Okay. So, hope this addresses your question. There are no other questions. Give us 5 more minutes to see if there are. So please ask questions which are relevant. So you can ask any question, of course. In a class, if I'm interacting with students, they can ask outside hours, outside the class hours. So of course you can feel free to ask. But if it is within and relevant, it would be more useful for the community to ask. Broad questions also you can ask. I can answer to the best of my ability. But by far, did you find the course productive, that you are able to learn a lot of ideas and concepts that you were not clear with earlier, or new material that you learned? I think if the answer is yes, then I would be happy because the purpose is served. And when we offer any advanced courses, this would be the prerequisite, because you should know this to take any advanced course like MMTSP 2 or 3 it is offered in the future. I we can buy the 530, but no question. Okay. So before we end this live session, so I really enjoyed. Okay, I get a question now. This is Parkinson's law. Can a series like Fourier series be formed by orthogonal functions by some level problem of orthogonal? Use whichever way you want to think about orthogonal functions and you expand them. I think it is perfectly fine, right? So, which Louisville actually is the Louisville. So, use whatever choice of your orthogonal functions you want. You can bring in whichever idea you want, but sines and cosines have a sort of natural meaning in terms of frequencies and stuff like that. But if you can bring in any other function, wavelet 2, for example, think about the R, it has a lot of harmonics, right? Infinite harmonics. So it depends on what you have in mind. The choice of the functions depend on the support, regularity conditions, etc. that you want to impose on the signal. Your choice, what you want. Please offer the course for digital communications. Aren't there courses in NPTEL that offer digital communication theory. There should be one course from IIT Kanpur, right? I don't know. I have not gone through the entire brochure of courses offered. So if there is anything complementary that we see, we can offer it. So I'll take this as feedback. If there's anything that because they're offering neural networks to NPTEL. So I think you have to watch out for this course in the August term. So for fall, we are offering the neural networks and learning systems part 1. So this could be a very useful course now, since a lot of people are talking about AI and stuff. This would be interesting. So digital communication theory, I would be happy to offer, but if you have to see what is there already. So if the contents are already there, then we may not offer that course. But if there's something else which we can expand on, I would be happy to take your comments, and I can offer this course in the future. Okay. So I enjoyed working with you in this course, and I hope you benefited from the videos, from the lectures. So feel free to give your likes and comments on the videos on YouTube. So we'll look at these comments. We may not be able to address all the questions immediately because of the lack of bandwidth, but we will surf through these during summer, and as far as possible, we'll try to answer your questions on YouTube. And this is really true democratization of education, where anybody can ask questions, and the instructor can answer all of you, right? And I hope the learning was very useful for you, particularly the homeworks. So I think more than the exams we gauge you, but homeworks is where you learn a lot. So if you've done your homeworks sincerely, I think you will benefit. So I think hope the problems were useful and you learned from this, and you can use it for anything, from your gate to your UPSC or any other exam, or as even a ground for more advanced courses you can take. But it's at the graduate level. I mean, I don't expect this course for the undergraduate level. This is at the graduate level, and that is the purpose of this. The introductory graduate level course in signal theory that you should be comfortable. So I think that was our purpose, and if you found this useful, I'm glad. And I hope the TAs have answered all your questions, because they worked behind the scene. 4 TAs worked diligently to set the problems carefully, to prepare the, we had these discussions, and preparing the solutions, and making sure the syllabus was sort of covered. I mean, those weekly lectures, the problems covered the weekly lectures, right? I think this is happening at the background, and I hope you found this useful, and spread the word around. We need more people to enroll into these courses, get credit, and with this we can build step by step the foundations in processing and communication area, and that all of you in India and around the world can benefit from this. Okay, with this I will end this, and if you have any questions, we will take this offline. So good luck for your exams, and I hope to see great scores from all of you. Okay? Wish you all the best.